Okay, class. In this lesson, we're going to be learning the fundamental theorem of algebra. We're going to learn the number of solutions to any polynomial equation and use what's called the conjugate theorem to find other solutions. It's a very simple theorem. It states that if we have a polynomial of degree n, there are exactly n solutions for this equation, f of x equals 0. So, solutions, other names for it, zeros, factors. Now, there's a little caveat. When we say there are exactly n solutions, we are counting repeated solutions, whether they're real or complex. So, for example, here, if we expand this is a polynomial. This will be a polynomial of degree 4. X to the third times another x will give us a degree 4 polynomial. If we expand it out, we see here we have three factors which are the same. We call them repeated factors. So altogether we have four factors here. We have four zeros. We get four solutions for f of x is equal to 0. Four zeros, again counting the repeated zeros. So in this example here we have a equation here. This is a degree 7 polynomial. Therefore there are 7 solutions counting any repeated ones there may be. There may not be any repeated ones, but in this case, we would have 7 solutions. In this case, f of x, 1/2 x to the 6th power. This is our highest degree term. Polynomial to degree 6. We have 6 zeros for this function here. Okay, so try these out. These are very simple. I'll give you just a few seconds. I'll even talk about these. Highest degree, degree 4. 4 different solutions. Highest degree, degree 11. 11 different zeros. Okay, conjugate theorem states, and this is assuming all real, I should make this down, all real coefficients. If a plus bi is a 0, if we have a complex number as one of the zeros, then its conjugate, a minus bi, is also a 0. And you see the definition of a conjugate here. We have a plus bi, a minus bi. These are what's called conjugate pairs. We have an additional case if we have only rational coefficients. So kind of a restriction beyond this original one where this theorem here is if we have all real coefficients. If one of them's complex, we have another conjugate 0 as well. If we have rational coefficients, if one of them is irrational of this form a plus square root of b, then we also have this other one, a minus square root of b. That's also a 0. These are called conjugates as well. So we can apply this. Let's write a polynomial function with a 0 at 2, a 0 at 3 minus 2i, and a leading coefficient of 2. So first of all, we recognize there must be another 0. We must have its conjugate pair. We're going to write this in intercept form, where this 2 here is our leading coefficient right here, 2. This 0 of 2 leads us to this factor, x minus 2. This 0 here leads us to this factor. This other 0 here leads us to this factor. Now we're going to combine, we're going to multiply this out. And I'm going to do this in a certain way. What I'm going to do is I'm going to take the x minus 3 and combine them together. Distribute this minus sign across here. This becomes a plus 2i. Here, x minus 3 is grouped together. This minus sign here is distributed over here. We get minus 2i. Now, if you see here, we have kind of an a plus b, a minus b structure. So that's our difference of perfect squares, a squared minus b squared. Now, minus 2i squared is actually equal to negative 4. Minus negative 4 is equal to positive 4 plus 4. We expand x minus 3 squared out to this, and then we're going to add this together. Multiply it all out together, and then we get our simplified solution there. Okay, so that's our lesson for today. There is this one problem over here for you to work out. I'll show the answer in 4, 3, 2, 1. Okay, have a good day, everybody.